In this video, I introduce normalizing flows for variational inference. Consider a general probabilistic model with observations x, latent variables z, and model parameters theta. Using phi theta to approximate a posterior distribution, the variational principle obtains a lower bound of the log likelihood as shown here. This log likelihood, this lower bound, where p theta is a likelihood and pz is the prior over the latent variables, and f is a negative free energy or the evidence lower bound. The first term, as shown here, is the k-error divergence between the approximate posterior and prior distribution, and the second term, as shown here, is a reconstruction error. This lower band provides a unified objective function for optimization of both the parameters theta and phi as shown here of the model and variational approximation respectively. Amortized variational inference method combines Monte Carlo gradient estimation and inference networks to solve the optimization problem. We focus on using normalizing flow to construct a complex posterior distribution. Deep latent Gaussian model is a deep directed graphical model that consists of a hierarchy of L layers of Gaussian latent variables, ZL for layer L. The latent variables in each layer depend on the layer above in a nonlinear way, and the nonlinear dependency is described by a deep neural network. The joint probability model is defined as here and explained in this figure, where F is a smooth mapping. The prior over latent variables is a unit Gaussian, as shown here, and the observation likelihood P theta is any appropriate distribution that is a condition on ZL and is modeled by a deep neural network. This is a deep latent Gaussian model. This is a normalizing flow layers. This is a inference network, and this is a generative model. Inference network maps the observations x to the parameters z of the flow as shown here. Generative model receives the posterior samples z from the inference network as shown here to reconstruct the observations x prime during training time. A normalizing flow is a transformation of a probability density through a sequence of k invertible mappings. For example, the initial density flows W0 go through the sequence of invertible mappings, and the output of the sequence is a complex probability distribution WK as shown in here. An invertible and smooth mapping F satisfies this equation. If the mapping F is used to transform a random variable z with a distribution QZ, the output random variable z prime has a distribution as shown here. Composing several simple maps and successively applying the transformations can construct arbitrary complex densities. Density Q key obtained by successively transforming a random variable z0 with a distribution q0 via a chain of key transformations fk is expressed as shown here. The expectations with respect to the transformed density q key can be computed without explicitly knowing q key as shown here. This is q0, which is no necessary computing the log determinant Jacobian terms if h doesn't depend on q key. The normalizing flows provide a way to approximate posterior distribution q for variational inference, selecting appropriate transformation f key and simple initial factorize the distribution, for example, independent Gauss distribution. The normalizing flows of different lengths are applied to obtain increasingly complex and multimodal distributions. Continuous normalizing flow is defined through ordinary differential equation as shown here and explained in this figure, where Vt is a vector field if C in F applies a continuous transformation to define the evolution of probability density through a velocity field. Consider the following transformation based on a neural network as shown here, where lambda are free model parameters and h is a smooth element-wise non-linearity with a derivative h prime. The log determinant Jacobian is computed using this equation, where psi is calculated from derivative of h times w. The density q key is implicitly given by this formulation. If the posterior distribution is approximated with the normalizing flow of length k, the posterior distribution q phi is the same as q key. The free energy F is written as expectation over Q0 as shown here. Q0. An inference model is constructed by using a deep neural network to build a mapping from observations X to the parameters of the initial density Q0 sampled from normal distribution, as well as parameters of the flow lambda. Using an inference network, a single computational graph allows to compute all the gradients of parameters to the inference network and generative model. The estimated gradients are used in conjunction with preconditioned stochastic gradient-based optimization, where parameters are updated by using this formulation with a diagonal preconditioning matrix theta that adaptively scales the gradient for the faster minimizations. As shown here, this is the pseudocode of variational inference with normalizing flows. For more details, please check with these references. Thank you. Bye.